Okay. All right, so guys, so welcome back. So this will be the lesson number 2 for our A2 syllabus. Okay, so let's do a very quick recap. Let's do a very quick recap. So what we have learned in the last lesson. In lesson number 1, we actually started on a concept called lattice energy. We learned what is lattice energy. Okay, so lattice energy, what is the key? We want the gaseous ion. We want the gas ion to combine with with the gas ion, so that they will become a solid ionic compound. Okay. So when the gas ion combine together to form solid ionic compound, they will release energy. So this energy they release is called lattice energy. The symbol is delta H, LATT. LATT stands for lattice. So we also learned in the first lesson that lattice energy must be exothermic. Okay, lattice energy must be exothermic. So you always see a negative value when you come to lattice energy. Why? When gas ion and gas ion combine together, okay, they will form a bond. Okay, they will form bond. So this bond is ionic bond. So we learned back in high school, when we form a bond, no matter the bond is ionic bond, covalent bond, hydrogen bond, whatever it is, formation of bond always release energy. Yeah. So formation of bond always release energy. So that's why the lattice energy is exothermic. Okay. All right. So I also mentioned in the last lesson that lattice energy can tell us the strength of ionic bond. So lattice energy can also tell us the strength of the ionic bond. Okay, it can tell us whether the ionic bond is strong or weak. So what's the logic here? The more exothermic, so the more exothermic the lattice energy. So if the lattice energy become more and more negative, it means that you have a stronger ionic bond. Okay, so that's everything we learned. So what else we covered in the first lesson? So in the first lesson, we also learned that there are two factors. Okay, there are two factors that actually can affect, okay, two factors actually affecting the lattice energy. So lattice energy is affected by two things. The first one is the charge. Okay. The second one is size. Okay. So this charge is referred to the charge of the ion. The size is also referred to the size of ion. So we learned that lattice energy is directly proportional to the charge. So when the charge is greater, the lattice energy also greater. Yeah. So then lattice energy is inversely proportional to the size. The bigger the size of the ion, the lower is the lattice energy. So that's what we learned in the first lesson. Okay, if you need to do a revision on that, please do so. Okay, so what else we learned? The last thing we learned in lesson number 1 is that we're talking about ion polarization. We learned about ion polarization. So ion polarization is a phenomenon. It's a special situation whereby a big size anion will be pulled by the cation. When this big size anion pulled by the cation, the anion now will become stretches. We will stretch the anion and change the shape of the anion. Initially, anion is in a sphere. So when we stretch the anion, the anion now will become like ellipse. The shape will become ellipse. So this ion polarization, we use it to explain the thermal stability. We use this concept to explain the thermal stability of your group 2. So we learned this in AS. We need to know thermal stability for group 2 carbonate and also group 2 nitrate. So that's it. So that is everything that we learned in the last lesson. Okay. So for today's lesson, we're going to do a lot of calculation. So we'll do some calculation. All right. So what we need to learn today is this. So everyone listen carefully. Yeah. So in the last lesson, we learned about the theory of the lattice energy. We learned what is lattice energy all about. Yeah. So today we will learn the calculation. of lattice energy. We will learn how to calculate the lattice energy. Okay, so that is the main focus for today. So if you want to do the calculation of lattice energy, you need to use a special method. Okay, you need to use a special method. This special method, okay, going to show you here. All right, this special method is actually called Born-Haber cycle. Okay, so Born-Haber cycle is used to calculate the lattice energy. Okay, so everyone can look at here. Born-Haber cycle is used in the calculation that are related to lattice energy. So when you want to calculate lattice energy, we will use Born-Haber cycle. So before I teach you guys what is Born-Haber cycle and how to do it, so there are a few important concepts we need to learn first. Okay, so we need to learn two important concepts, yeah, before we jump into the what we call that the lattice energy. Okay, so the first concept that we will learn today is called enthalpy of atomization. Okay, so we need to spend some time to learn enthalpy of atomization first. Then we will learn about electron affinity. Only after we cover these two concepts, then only we can work on the lattice energy. Okay, so that is what we need to do. So we're going to go step by step. Okay, let's start with the first one. So the first thing we will learn today is called enthalpy of atomization. So enthalpy of atomization, the symbol is a delta H, and then you're going to see the subscript AT here. AT is the short form for atomization. So you see a circle on top. This circle, we call it a knot. So as what I told you all before in the last lesson and also in AS, when you see the knot here, it means that this calculation is carried out in standard condition. Okay, so we are doing the calculation in standard condition. So let's do a quick revision. What do we mean by standard condition in chemistry? Temperature must be 25 degrees Celsius. The pressure must be 1 atmospheric pressure. Okay, so we do the experiment and we carry out the calculation at this temperature and this pressure. That's why it is under standard condition. Okay, so that is what we need to do. All right. So, okay, make sure everyone know the symbol, okay, for this. Okay, so now let's look at the definition. What is the definition for enthalpy of atomization? So they love to ask you all the definition. So make sure you know about it. So enthalpy of atomization, okay, the keyword very simple, atom. You want to make something become atom. Okay, atomization, you want to make something to become atom. So enthalpy of atomization is defined as the energy that required to produce 1 mole of gaseous atom, okay, from its element. So element means raw material. So you use some raw material and you change the raw material to become gas atom. And the energy that you needed for this process to take place is called enthalpy of atomization. So the keyword is 1 mole of gas atom. Okay, so up to this point, do you guys understand what I've taught you so far up to this point, enthalpy of atomization? Okay, all right, good. Okay, thank you for responding. So it's not very hard. So the idea is very simple. Atomization, we want to get the gas atom. Okay, we want to get the gas atom. Okay, so there's a few things you need to know. Okay, first of all, I want to show you this equation first. I want to show you the equation. So let's say I want to write the equation for the enthalpy of atomization for lithium. I want to change the lithium to become gas atom. So what should I do? I start with this. Okay, I start with this. So I start with the lithium first. So remember, I said I mentioned in the last lesson, in this chapter, it is compulsory to write state symbol. In this chapter, you like it or not, you must go to write the state symbol. It is so important. In AS, most of the time, you don't need to write state symbol, but it's not for A2. Okay, for this chapter, you must write the state symbol. So let's start with lithium. Okay, let's start with lithium. So lithium, originally, okay, it is in a solid form, right? Lithium is a metal, right? We know lithium is a metal. And generally in chemistry, metal always in solid form. So now we have a lithium solid. we want to change the lithium solid to become lithium gas atom. Okay, so this particular process is called enthalpy of atomization. Okay, this is enthalpy of atomization. You want to change the element, you want to change something. In chemistry, we don't call it something lah. Okay, we call it element. Okay, we want to change the element to become gas atom. And remember, the gas atom must be 1 mole. We need 1 mole of gas atom. Okay, if you get 2 mole of gas atom, that is not atomization. Atomization only need 1 mole of gas atom. Okay, so the energy that you needed for this process is called enthalpy of atomization. So let's say I give a figure, positive 140 kilojoules per mole. This number no need to memorize. Okay, so what does this number means? We need to use 140 kilojoule in order to change the lithium from solid to become lithium gas atom. Okay, so that is atomization. Okay, so let me show you another 2 more example, which is written here. Okay, so the second example is chlorine. Okay, so let's start with this, everyone. So chlorine, okay, I want to do the atomization. So let's say I want to do atomization of chlorine. So everyone, let's start with chlorine. Chlorine, the formula is Cl2. Okay, chlorine exists naturally as a molecule. Chlorine exists naturally as molecule. So chlorine, it is a gas. Chlorine is a gas in the most nature form. So now you want to change the chlorine gas molecule to become chlorine gas atom. Because many students, they say, sir, this is gas, this is also gas. Is this still atomization? Yes, atomization, you want to produce 1 mole of gas atom. So you don't care over here is solid, liquid, or gas. You don't care. As long as at the end of the day, you produce 1 mole of gas atom, that is already atomization. Okay, so that's it. So how to balance it? So we need to put a half here to balance it. Then only you get this equation. So this is atomization of chlorine. Then some student will ask, Mr. Martin, why don't we put a 2 here to balance it? You see, so you have 2 chlorine here, we have 2 chlorine. So why don't we put 2 to balance it? So what's the problem here? Remember, when we want to do enthalpy of atomization, we always want to produce the gas atom of 1 mole. We only need 1 mole of gas atom. If you go to put 2 here, this equation is balanced. Absolutely, no problem. The equation is balanced. But if you write in that way, you are getting 2 moles of the gas atom. We don't want that. We only want to get 1 mole of gas atom. So that's why we cannot put a 2 here. It couldn't be written in that way. So to get enthalpy of atomization, the gas atom must be only 1 mole. So since the number here must be 1, we only can balance the equation by changing the number here and make it become half. So guys, can you type in the chat box and let me know, are you okay with this concept? Can I? All right, good. Good. Okay, thanks for responding. Okay, let's do one more thing. Okay, what if now we want to do atomization of bromine? So what if now I want to atomize bromine? Okay, bromine, the formula is Br2. Okay, bromine exists as a liquid naturally. You learned this back in high school. Chlorine is a gas. Bromine is a liquid. Iodine is a solid. Okay, so bromine exists as a liquid naturally. Now we want to change the bromine to become bromine gas atom. So remember, atomization, we always want to get gas atom. How many gas atom we need to get? 1 mole. Okay, so in chemistry, the number 1 no need to be written. So you don't want to show the 1 here. Don't need to show the 1 here. Okay, so some students ask, so what if I show number 1 here? Would they penalize me? Would they penalize you? No, they won't. They won't. So to balance the equation, you need to put a half here. Settle. Okay, so this is atomization of bromine. You change the bromine to become gas atom. How many gas atom? 1 mole. So now we are done with the concept for enthalpy of atomization. Okay, so you see, I use 3 examples. I want to change the lithium from solid to become gas atom. I want to change the chlorine from gas molecule to become gas atom. I want to change the bromine from liquid to become gas atom. It doesn't matter you're starting with a solid, liquid, or gas. It doesn't matter as long as at the end of the day, you are getting gas atom and they are 1 mole, and that is enthalpy of atomization. So now I want to give you a tips here. So everyone need to know this. So in chemistry, you must know enthalpy of atomization. It must be always in a positive figure. It must be always in a positive value. Positive value, we also can say it is exothermic. So now we learned 2 things already. Yeah? Lattice energy must be negative. Enthalpy of atomization must be positive. Okay, don't memorize blindly. You need to understand the reason behind. Why? Why enthalpy of atomization must be positive? Because remember, for atomization, what we want to do, we want to get the gas atom. We want to get gas atom. If you want to get the gas atom, you need to break the bond. Example, this is a chlorine. If you want to get the gas atom, you need to break the bond. So we learned that in high school, if you want to break the bond, you need to absorb the energy. You need to use the energy to break the bond. Yeah, you need to use the energy to break the bond. Okay, so breaking bond always absorb energy. Absorb energy means that it is always endothermic. You need to absorb energy means endothermic. Endothermic is positive. So that is the reason. Okay, so what if you got a question in your A-level paper? They ask why enthalpy of atomization is always positive. So this is the answer. Okay, because energy must be supplied in order to break the bonds that holding the atom together. Okay, so if you want to do atomization, you want to break the bond. Only when you break the bond, then only you can get your gas atom. Okay, all right, so up to this point, so far so good, everyone? Okay, great. Okay, so now done already. So now let me show you some sample question here. I'm going to show you some sample question before we jump on to electro affinity. Okay, so now I'm going to give you some extra knowledge. So guys, let's take a look here, extra knowledge. So what if the question asks, what is the enthalpy of atomization for helium? So if we have a helium, what is the enthalpy of atomization? So the answer is 0. Why? Because we know helium, neon, argon. We learned this before back in high school. They belongs to noble gas. Noble gas is the last group in the periodic table. So all the member in noble gas, they exist as monoatomic gas. Monoatomic gas, which means what? All the noble gases, let it be helium, let it be neon, let it be argon, they are all in gas form already, and they already exist in a single atom. Since they already exist as single atom, you don't need to break the bond anymore. You only need to break the bond. For example, this is oxygen, O2, oxygen gas. You need to break the bond to get the atom. Nitrogen gas, you need to break the bond to get the atom. But for all the normal gases, they already exist in atom form. They already exist as a single atom. So there's no point and there's no need for us to use additional energy. We don't need to spend any energy to break the bond. Because why I need to break the bond? They already in gas atom. They have no bond for me to break. Okay, there's no bond to be broken. So no need. Okay, so this is the one. Okay, so this one, make sure everyone know, yeah? If anything not sure, please feel free to ask me, yeah? Okay, now I want to show you another one more important concept. This concept we will use it quite a lot later on when we do the Born-Haber calculation. When I demonstrate the Born-Haber calculation later on, you guys were able to see this, okay? So how to use the bond energy to get the value for enthalpy of atomization. Sometimes they don't give you the enthalpy of atomization directly. Okay, sometimes they won't give you the value for enthalpy of atomization. So you can use the bond energy to obtain, to get the value for enthalpy of atomization. No worry, you will see this when we do calculation later on. So now I teach you a simple concept. So this is the formula we use. To find enthalpy of atomization, you just take the bond energy, you multiply by half. That's it. Just take the bond energy, multiply by half, you will get enthalpy of atomization. This only works if and only if you have a diatomic molecule. If you're given a molecule, this molecule have two atoms, then only you can use this concept. Okay, what do we mean by diatomic molecule? Any molecule that got two atoms like Cl2, O2, Br2, I2, N2. All these molecules, they are made of two atoms. So we call them as diatomic molecule. Okay, so only when you have diatomic molecule, okay, you go to take their bond energy. Okay, where you can find the bond energy, you can get from data booklet. Okay, for the latest version, they might not give you the data booklet in exam. They will directly give you the bond energy in the question. Okay, but when you do your normal practice, always use the data booklet. So I hope you guys know where to get the data booklet. You can download the data booklet from, you know, the Google search engine. You just type 9701 data booklet, okay, in Google. You'll be able to search for this, okay? So which they will give you something like this. This is the data booklet like this. You can see here, yeah? So these are the bond energies that we will use, okay? So take the bond energy, multiplied by half, then you will be able to get the enthalpy of atomization, as simple as that. So what's the logic? Why we can multiply by half? Why multiply by half, Mr. Martin? Why not multiply by 3? Why not multiply by 3 over 2? Why not multiply by 5 over 3? Why we multiply by half? Why is half? The idea very simple. So let's do a simple mathematics. You see, today, if you have a chlorine gas molecule, this is a chlorine molecule. Is chlorine a diatomic molecule? Yes, chlorine made of two atoms, so it is diatomic. So what is bond energy? We learn in high school, we learn in AS. Bond energy is the energy to break the covalent bond. So today, if you have chlorine, Cl2, chlorine, Cl2 means you have Cl and Cl joined together. So the bond energy means that this is the energy that we needed to break the bond. So we need 242 kilojoule to break the bond. Okay, where to get the energy from? This one you can get from data booklet. So let me show you here. For example, you see everyone? Chlorine, the bond energy is 242. Okay, so you need to use 242 kilojoule to break the chlorine. Okay, so now come back to here, everyone. So once I use 242 kilojoule to break the bond, so what I am getting? I'm getting 2 moles of chlorine gas atom, isn't it? I'm getting 1 and 2. I'm getting 2 mole of chlorine gas atom. So everyone type in the chat box. Let me know, is this 242, okay? This 242 is the energy to break the bond. And after I break the bond, I get 2 mole of chlorine gas atom. So my question to all of you, is this 242 enthalpy of atomization? Is this enthalpy of atomization? Answer yes or no in the chat box. Okay, fantastic. Very good answer. The answer is no. Why? Because if I want to get enthalpy of atomization, I only need 1 mole gas atom. Now, yes, I already break the bond. The bonds are broken, but when the bonds broken here, it result in 2 mole of gas atom. I don't want 2 mole of gas atom lah. I need 1 mole of gas atom only. Okay, so what should I do? So if you want to get 1 mole of gas atom, let's do a mathematics. How to change the 2 here become 1 mole of gas atom? The entire equation multiplied by half. The whole equation multiplied by half. Because if you take half multiplied by Cl2, the equation becomes half Cl2. If you take the half multiplied by 2, you get 1. So you see, when everything multiplied by half, you already able to get 1 mole of gas atom, which is the enthalpy of atomization that we want. Since everything multiplied by half, the bond energy need to multiply by half as well. So this 242, you multiply by half, you will get 121. As simple as that. Actually quite simple, common sense. You see, when you break the chlorine, you get 2 mole gas atom, then the energy is 242. So which means 242 can give you 2 mole of gas atom. So if you only need 1 mole of gas atom, do you need so many energy? No need, right? You just need half of it lah. Okay, 242 can give you 2 mole of gas atom. So if I only need 1 mole of gas atom, I only need half of this energy, which is 121. Okay, so that's why we take the half multiplied by the bond energy. Okay, so I'm trying my best to explain to you why we multiply by half, why we don't multiply by other number. Okay, why we don't multiply by 3, why we don't multiply by 4, why we don't multiply by 7 over 2. Okay, why we only use 1 over 2, or we call it half, to multiply by bond energy. Okay, guys, please let me know in the chat box. Are you okay with this? Fantastic. Very good. Okay. So here everyone should know, sometimes in exam, they are super kind. They give us the enthalpy of atomization directly. Okay. But sometimes they are not. So if they don't give us the enthalpy of atomization, we must know where to get it, where to find it ourselves. So we need to use the bond energy, and we just multiply by half, and that's it. So we will be able to get the enthalpy of atomization already. Okay. So again, like what I said, don't worry. I will do this calculation with you later on. Later on, you can see at the bottom here, I'll show you the calculation, okay, how it works. Okay, I'll show you here how to do calculation. So don't worry on that. Yeah. Okay. Let's come back here first. Okay, so we are done with the first concept today. So we are all done with the first concept, which is the enthalpy of atomization. So that's it. So you all just need to know the definition for enthalpy of atomization. You all need to know how to write the equation for the enthalpy of atomization. You all must know enthalpy of atomization must be always positive. You all need to know that if the enthalpy of atomization is not given, you can use the bond energy multiplied by half to get the value yourself. That is everything you need to know for now. Okay, so later we will put all these puzzles together to do the calculation all together. Yeah, later we will do this calculation together. Then you will have a better idea. Okay, all right. So now let's go on with another concept. Okay, let me teach you another concept. Then we can start with the calculation already. The second concept is actually called electron affinity. Okay, electron affinity. Yeah. So electron affinity, the symbol is EA. E is electron, A is affinity. Sometimes, most of the time, they just write EA, or sometimes they go to write delta HEA. Same thing lah. Electron affinity. Yeah. So what is electron affinity? So you all must know electron affinity is exactly opposite to ionization energy. So you learn about ionization energy back in your AS syllabus. In AS syllabus, you learn about ionization energy. So now in A2, you will learn about electron affinity. So let me write it out like this. Okay. So in AS, you will learn about ionization energy. So when you come to your A2, you will learn about electron affinity. So I would say if you guys fully understand ionization energy inside out, if you fully understand what is ionization energy all about, you shouldn't have a big issue to understand electron affinity, because it just go opposite. Okay, what do I mean? Okay, let's do a quick 3 to 5 minute revision on ionization energy that we learned in AS. So let's spend 3 to 5 minutes to do revision. So ionization energy is the energy we needed to remove the electron. Okay, the energy we needed to remove the electron. So we want to remove the electron. Okay, example. Okay, we have a gas atom A. So this is gas atom A. So we want to remove 1 mole of electron from the gas atom A, so that the gas atom A now will become gas ion. And this gas ion, the charge is +1. The energy that we needed to remove the electron away is called ionization energy. Okay, so ionization energy is the energy that we need to remove the electron away, okay, from the gas atom or the gas ion. Okay, so in order to form the gas ion. Okay, so let's do a quick revision here. So what if the question asks us, okay, this is something about AS. So if you don't know about this, you should do your revision for your AS seriously. So let's do a quick revision here. So what is, okay, the question asks, write the equation, okay, write the equation to show the first ionization energy of aluminium. So how to write equation to show the first ionization energy for aluminium? So for ionization energy, you must always start with this aluminium. So aluminium, everything, when you come to ionization energy, it must be in gas form. So you have aluminium gas atom. So now you want to remove 1 mole of electron from aluminium gas atom. So the 1 mole of electron you remove, you put it here. So when you remove 1 mole of electron from aluminium gas atom, you become aluminium positive 1 and gas ion. So this is the first ionization energy. We learned this in AS. So what if the question asks me to write the equation to show the second ionization energy for zinc? So what should I do? So when you want to go for second ionization energy, you're starting with this. You're starting with the zinc. But now the zinc is still in gas form because ionization energy, we always remove the electron from gas. No liquid, no solid, must be gas. So what you want to do? So for second ionization energy, you want to form Zn2 plus. So it always matching one. Second, here must be 2 plus. First ionization energy, it must be plus. Third ionization energy must be 3 plus. It always matches. Okay, it always matches. So what you should do? So if this is 2 plus, this one, the charge must be 1 unit lesser than this. If this is 2 plus, this one is positive. Make sense, huh? You have Zn plus gas ion. I put my hand in, remove 1 mole of electron. Then once I take 1 mole electron away, you become Zn2 plus already. Okay? And then this is the electron which I removed away. So this concept is called ionization energy. So can you guys please type in the chat box to let me know, are you guys still clear on this concept? Okay? Because again, guys, it has nothing to do with A2. This has nothing to do with A2. This is entirely AS. This is purely AS. So now, why I say if you fully understand ionization energy, you won't have a big issue when you come to electron affinity. Because electron affinity just do something exactly opposite. What do you mean by exactly opposite? So for ionization energy, we want to do the removal of electron. So when we come to electron affinity, we do the other way around. Here we take the electron away. Here we go to pump in the electron. We go to put in the electron. So we call it receiving electron, or you can call it gain electron, or you can call it accept electron. That's it. Okay. So in ionization energy, we want to remove, or you can use the word donate, or you can use the word release. So we want to throw away the electron. But when it comes to electron affinity, we want to take in the electron. So that is the only difference. So look at here. So as what I say just now, ionization energy focus on removal of electron. Electro affinity go exactly opposite. We want to gain, or we want to add in the electron. We want to put in the electron to the substance. Okay. So same thing when, so this is the revision that we do previously. So first ionization energy and second ionization energy. You learn this back in AS. Okay. So first ionization energy, you want to is the energy required to remove 1 mole of electrons from 1 mole of gas atom, so that in the end you are producing 1 mole of gaseous ion. So what is the charge? It must matching. First, the charge will be 1 plus. So this is the equation. So you guys must able to write the definition for the first ionization energy. You also need to write the equation for the first ionization energy. So there are two important skills you must know. You guys must know how to get definition. You all must know how to write the equation. You need to know both. Yeah, you need to know both. So what about this? Second ionization energy, same thing. Second ionization energy in AS, we learned this, is the energy that we require to remove 1 mole of electron. So we always remove 1 mole of electron. It cannot be 2 mole, it cannot be 3 mole, must be 1 mole. So we remove 1 mole of electron from 1 mole of gas ion. This gas ion is 1 plus. So when we have 1 plus ion, we take away 1 mole of electron from them. So we will be able to produce 1 mole of gas, 2 plus ion. So you see it matching one. Second ionization, the charge is 2 plus. Okay? So this is everything about AS. This is AS. Now, how are we going to marry this concept to A2? How to borrow this concept to A2? So like what I say, ionization energy, remove the electron. So what about electron affinity? So electron affinity also got first, second, third, fourth, just like the ionization energy. Okay, ionization energy, you have first ionization, second ionization, third ionization, and so on. Same goes to electro affinity. You have the first electro affinity, second electro affinity, third electro affinity. Same concept applies here. Okay, so what you need to know here. So let's have a look. So let's look at here, guys. Come on. What is first electro affinity? So first electro affinity is the enthalpy change. Okay, we use the word enthalpy change. We don't use the word energy required. We don't use the word energy required. I will tell you guys why in a short while. Okay, I will explain why we don't use the word energy required, why we use the word enthalpy change in a short while. So first electron affinity, we call it EA1, electron affinity, first one. Okay, so first electron affinity also can be written in this delta H electron affinity number 1. Okay, you can write in that way. So electron affinity, the first one is this, the enthalpy change for you to add 1 mole of electrons to 1 mole of gas atom. Okay, so you see, we go the other way around. So when you have a gas atom, if you put your hand in to remove 1 mole of electron, take out. So this is called ionization energy. Today, if you go the other way around, if now you still have 1 mole of gas atom, but you are putting the electron, you put in the electron to the gas atom. So this is called electron affinity. So when you put in 1 mole of electron to the gas atom will become negative ion, which is 1 minus. Okay? So it just go exactly opposite as your ionization energy only. So look at here. Okay? So electron affinity is the enthalpy change, okay, to add 1 mole of electron into 1 mole of gas atom in order to form 1 mole of gas ion. The gas ion, the charge is 1 minus. So you see, it's still matching. First, the charge still 1. The only difference is affinity. The charge is negative. If ionization, the charge is positive. Okay, guys, let me know in the chat box. So far, so good? Okay, simple as that. So now, same thing, you not only need to know the definition, you also need to know the equation. Okay, so let's say I use an example here. So let's say the question asks, Martin, can you please write the equation for the first electron affinity of substance Z? So how to write the equation? So remember, electron affinity or atomization energy is all about taking or remove the electron. No matter you want to donate electron or receive electron, it always happen in gas form. It always happen in gas form. And as what I mentioned earlier on today, in this chapter, state symbol is very important. State symbol is compulsory. So you must write the state symbol. So you must start from a gas. So for first electron affinity, you want to start from a gas atom. So we have a gas atom called Z. So now you put in 1 mole of electron inside. So we go to add 1 mole of electron. So we add 1 mole of electron into the Z. The Z now will become positive ion. Sorry, it will become negative ion. Sorry, my bad, my mistake. Sorry for that. Become negative ion. And it's still a gas. So everything happened in gas form. So this is called electron affinity. So look at the example I give you in the notes here. I use the B lah. So I have a compound B. So I have a B atom. It is in a gas form. So the gas atom B receive 1 mole of electron and it produce 1 mole of gas ion. This gas ion is -1 in the charge. So this concept, the energy that we needed to make this happen is called first electron affinity. Okay, so guys, can you please let me know in the chat box? Do you able to follow? Do you understand what I taught you so far up to this point? Okay, all right, good. So now when you understand first electron affinity, you shouldn't have any issue with second electron affinity, okay? So second electron affinity is you copy paste the entire thingy here, copy paste the entire definition, put it here. So second electron affinity is the enthalpy change to add 1 mole of electron to, so now you want to add the electron to where? To the gas ion already. Remember, first of all, you're starting with a gas atom, you put in 1 mole of electron. When you put in 1 mole electron, this gas atom already become a gas ion. And this gas ion is -1 in the charge. So when you want to do it for second time, when you want to do a second electron affinity, you want to do the same thing for second time, you still put 1 mole of electron, but this 1 mole electron you need to put into the gas ion already, okay? So that's why I changed the definition here. This 1 mole of gas atom now become 1 mole of gaseous ion. This gas ion is -1. So when you pump in 1 mole of electron into the ion, the -1 will become -2. So in the end, you will produce 1 mole of gaseous 2- ion. So same thing is still matching, right? Second electron affinity, the charge is 2-. Okay? So again, allow me to remind you one more time. Electron affinity, you will get negative charge. Ionization energy, you get positive charge. As simple as that. So this is the equation. You all can see. Yeah, this is the equation here. All right. So we have a B negative gas ion. We pump in 1 mole of electron to it. So when 1 mole electron go in, this ion will become B2 negative. So same thing like what I keep mentioned just now, all the electron affinity or ionization energy, it always happen in gas form. It always take place in gas form. Okay, so that is what you need to know. All right, with that being said, we are done with first and second electron affinity. So now I want to show you guys a very important concept. Okay, so this is a very important concept, and this is a very common question in the A-level examination. Okay, this is a very, very common question in the A2 examination. All right, so what it is? Okay, so you all must know first electron affinity must be exothermic. First electron affinity, when you first receive 1 mole of electron, it is always exothermic, always release energy. Then the subsequent one means what? Second electron affinity, third electron affinity, fourth electron affinity, and so on. They are endothermic. Okay, so the idea is this. Only the first electron affinity is exo. All the subsequent one, second, third, fourth, and so on, they will be positive. Okay, so this is a very popular question in exam. You must know why. Why the first electron affinity is negative and the subsequent one will be positive. So let's start with this. So the first one, so let me explain to you guys why the first electron affinity has to be negative. So everyone put your eyes on here. So when you do first electron affinity, what happened? You have a gas atom, which is neutral initially. So when you do first electron affinity, that is the first time you put in the electron. When you put in the electron to the gas atom, what happened? So you want this electron and the gas atom to form attraction. Make sense? If you don't have attraction to pull in the electron, this electron will get out anyway. Okay, you always, okay. So just imagine like this. So this is a surface. I want to let the electron come in. So I put some glue at here. I put some glue on the electron, and I want the electron to glue into the gas atom. So glue means they stick together. When you want to stick together, you need to form some attraction, right? You want to have some attraction force. Okay, you want to have some attraction force. So when you form any bond or form any attraction, you always release energy. That's it. Remember, forming attraction, release energy, breaking the attraction or breaking the bond, absorb energy. So when you do first electro affinity, you want to pull in the electron. When you want to pull in the electron, you need to attract the electron. You must attract the electron into the atom. So when you want to attract the electron, you need some attraction force. So when you want to form the attraction, okay, when you want to form any attraction, okay, you need to release energy. So that's it. Okay. So guys, did both of you understand why the first electro affinity is exothermic now? Why the first electro affinity is exothermic? Are you okay with that? Okay. All right. Thank you for responding. So very simple. So when I want to do first electro affinity, I want to pull in one more of electron. When I want to pull in one more electron, I need to form attraction. I need to attract the electron. Okay. Any formation or any creation of this attractive force, when you want to create, when you want to have that kind of attractive force, you need to release some energy. Okay, because makes sense, ma. If you go to absorb energy, when you absorb the energy, it looks like a knife. You will go to break the bond. No point lah. Why you want to break the bond? You break the bond here, then this electron cannot come in already. Yeah, so cannot. So you are not absorbing the energy, but you want to release. Okay, now this is something very interesting already. Why the subsequent one? Why second electro affinity, third, fourth, and so on, they are endothermic? Because of this. So everyone put your eyes on this second diagram. Look at this diagram. So when I want to do second electron affinity, just imagine if I want to do second electron affinity, what happened? I want to put one mole of electron, which is this fella, into this ion. Okay, I want to put one mole of electron into this ion. So what happened? So look at here, everyone. So this is the gas ion, which is 1 negative in charge. So now I have one mole of electron. I want to put it in. So this is my second electron affinity. Okay, by right, that is what it should be. Okay, but what's the big issue here? When you want to put one mole of electron to the gas ion, what happens is this. This ion, the charge is negative. Electron also negative. So when negative and negative, they met together, what happens? So we learned before in high school, same charge repel. Same charge, they always repel. Opposite charge attract. So when I want to put this one mole of electron into this gas ion, okay? So when I put it here, this negative, negative repel. When I want to put it here, negative, negative repel, okay? So very hard. So they can't go in. This electron just can't go in because when it go in, it will automatically get kicked off, repel away, okay? So if I still want the electron to go in, I need to put in some additional force. So imagine I need to put a hand here. This hand need to apply some additional force so that I can push this electron into it, okay? This additional force that I need to apply, okay, will be the extra energy I need to absorb, okay? Because the energy won't come from nowhere, okay? We need to get the energy from somewhere. So this energy, we get it from absorbing the heat. We absorb some additional energy and use that additional energy to push the electron into the ion. Why we need the additional energy? Because this electron don't want to go into the gas ion due to repulsion force. So that is the reason. So how you put in a proper words, just assume what if this question came out this year? What if they ask you in the A2 paper this year? They ask why second electron affinity is positive or endothermic. So this is the answer. Okay. Extra energy is required in order to overcome the repulsion between the anion, which is this fella, and also the electron. So this anion and electron got repulsion. So we need to use extra energy to push this electron into the anion. This additional energy, it will make it endothermic. Okay, so that's the reason. Okay, that's why from second, third, and fourth, and so on, all the subsequent electron affinity, we always need the additional energy to put the electron into the gas ion. Because if you don't do that, no way the electron can go into the gas ion, because the negative ion and the electron, they always repel. They always repel each and other. Okay, so guys, so far, so good. Can understand, huh? Okay, I hope everyone can understand this, huh? Okay, awesome, awesome. Okay, cool. So let's go on. So the next thing, which is the last thing for electro affinity, then we will go on to the calculation already. This is the one. Okay, this is a new syllabus they added in year 2022. This is year 2022 new syllabus. Okay, so previously this part never been tested. Okay, so this is a new addition in year 2022. This is the trend of the first electron affinity in your group 16 and group 17. Okay, so no need to purposely memorize. It's a very, very simple idea only. So look at the group 16 and look at the group 17. No need to memorize because the periodic table is given. Okay, there is periodic table there. Okay, you have a periodic table. So that is that. So you don't need to memorize. So group 16, these are the member. Group 17, these are the member. And this is the electron affinity. All these number, no need to memorize. I just want you all to know the trend. No matter group 16 or group 17, when you're moving down the group, electron affinity decreases. Electron affinity decreases. Okay? Electron affinity decreases. Okay? So that is the idea. Okay? So why? Okay, why? Why electron affinity decreases when we're moving down group 16 and moving down group 17? Okay, so this concept is something like we used to learn in ionization energy as well. Okay, this concept we can borrow from the ionization energy that we learned before. Okay, see, when we're moving down the group, we have more and more shelves, right? Example, this is sulfur. This is selenium. All right, more and more shelves. Okay, going down the group, more and more shelves. Okay, so when more and more shelves, which means what? Now the electron is further away from nucleus. So imagine this is nucleus. This is nucleus. This is the electron that we want to receive. So we want to receive one more electron. We want to put it in. This is the electron that we want to put it in. Okay. So we learned this in ionization energy as well. When the electron further away from nucleus, the shielding effect becomes greater. Okay, so we have more and more circle, more and more shell, you have greater shielding effect. Greater shielding effect means what? You have more and more repulsion. Okay, you have more and more repulsion there. Okay, you have more and more repulsion. So when you have more and more repulsion, so what happened is this. So remember when you do first electro affinity, you want to form attraction with the nucleus. You want to form attraction with the nucleus. So you want to pull the electron in. So you want to form this attraction. Okay. So common sense, when the electron is far away from nucleus, you will form a stronger or weaker attraction. Guys, type in the chat box. When the electron far away from nucleus, you will form a stronger or weaker attraction force. Strong or weak? Okay, very good. Weak, right? Okay. When electron far away from nucleus, the force or attraction will become weak. So you will form a very weak attraction. When you form a weak attraction, you will release less energy. Because remember, I said early on today, okay? First, electron affinity, always negative, okay? Because we want to pull in the electron, we need to form the attraction with the electron, okay? So it always negative. So when the electron far away from nucleus, the attraction you form is a weak attraction. So when you form a weak attraction, you will release less energy. So when you release less energy, the enthalpy, sorry, the electro affinity, the value become lesser. You see? From negative 200, lesser, negative 195, lesser, negative 190. Okay? Same thing, group 17. Chlorine, when they form attraction with the electron, they release 350. So bromine, when they form the attraction with electron, only release 324. Iodine, when they form the attraction with electron, they only release 295. Okay, they release less and less energy. Okay, again, why? Let me use the group 17 for demonstration. Okay, let's, for example, you know, chlorine, the size is like this. Iodine, the size is like this. So for chlorine, the electron very close to the nucleus, you can form a strong attraction. When you form a strong attraction, you release more energy. Okay, you release more energy. That's why you release 348. Iodine, the electron very far away from nucleus. Okay, so when it's far away from nucleus, you only form a weak attraction. When you form a weak attraction, you release less energy. So that's why when iodine receives the electron, you only release about 300. Okay, so it's lesser than this. This is about 350. This is about 350. This is about 300 only. Okay, so simple as that. All right, so guys, are you okay with this concept? Okay, so let me run through this thing again with both of you. Okay, all right, when you get with you guys, okay? So let me run again with this one. So if they ask why, what is the trend of first electro affinity? Okay, what is the trend of first electro affinity in group 16 and group 17? The trend is what? The electron affinity become less exothermic. Okay, it become less exothermic, or you can say electro affinity decreases. Okay, all right, decreases, or you can write less exothermic is more accurate lah. Okay, so why? So going down the group, you have more and more shells. So the electron getting far away from nucleus, and it creates greater shielding effect. So because of these two reasons, the force of attraction between nucleus and electron become weaker. When you form any attraction, you always release energy. When you form a weaker attraction, you release less energy. Okay? When you release less energy, that's why the value becomes smaller. Okay? So that's why it becomes less and less exothermic. Okay? So that is what you need to know. All right. So we are done. So then, okay, the next thing we need to know is this. Okay, just now we are talking about moving down the group, right? We are talking about going down the group, moving down group 16, moving down group 17. Okay, we are moving down the group. Okay.
Teacher.
All right. Okay, hold on. Okay, thank you. So I will admit. Okay. Okay, good. Right. Thanks for reminding. Yeah. Okay. So now let's look at this. Okay, so this will be the last thing. Okay, just now we're talking about moving down the group. Now we want to see what happened when we move across the period. Okay, we learned this in AS as well. If this is periodic table, when you go from top to bottom, we call it moving down the group. When you go from left to right hand side, we call it move across the period. Okay, we call it move across the period. Okay, so that's it. All right. So now we want to see what happened here. Okay, just now we already see what happened when we go from top to bottom. So now we want to see what happened when we go from left to right. Okay. So moving across the period, okay, what will happen? Okay, so you were able to see the electron affinity, the value will change and become more and more negative. Okay, it become more and more negative. You see, compare same period like this. So this one release 200, this one release 350. You release more energy when you move across the period. Same thing, these two in the same period. Selenium only release 195, bromine release 320 something. All right. So moving across the period, the electron affinity increases. Okay, moving down the group, electron affinity decreases. Okay, so why? Why the electron affinity actually increases? Okay, there is a reason. So same thing, we can use those concepts that we learned in ionization energy back in AS to help us. Okay, that's what I say, guys. That's what I keep saying. Ionization energy and electron affinity, there are so many concepts, they are overlapping each and other. So if you understand ionization energy, you can use those concepts again, even you are doing electron affinity. So this is what we want to, this is what happened. So let's have a look here, everyone. Moving across the period, moving across the period, when I go from left to the right, there are more and more protons, isn't it? Example, okay, this is sulfur. Sulfur is 286. This is bromine, 287. So they have same number of shells. They have 3 circles each. Okay. So this one have 3 shells. This one also have 3 shells. Okay. So moving across the period, you have more and more proton, right? This fella, sulfur, got total 16 proton. Bromine got 17 proton. Okay, so moving across the period, you have more and more proton. Then the nuclear charge increases. So we know the nuclear charge is referred to the charge of proton. Okay, the nuclear charge is referred to the charge of proton because nuclear come from nucleus. So inside the nucleus, you have proton and neutron. Neutron don't have any charge. Only the proton got charge. The proton charge is positive. Okay, so this positive charge from the nucleus is called nuclear charge. So everyone take a look here. When you have 16 proton, the charge is positive 16. When you have 17 proton, the charge is positive 17. So when the nuclear charge increases, you can form a stronger attraction. So just imagine this electron is pulled by 16 Newton. This electron is pulled in by 17 Newton. So you can see bromine can form a stronger attraction compared to sulfur, right? Because bromine got more proton, so it can form a stronger attraction. So when you form attraction, always release energy. When you form a stronger attraction, you release more and more energy. As simple as that. That's what you can see here. Okay? Chlorine can form a stronger attraction than sulfur. Chlorine release more energy. Bromine can form a stronger attraction with the electron compared to the selenium. That's why bromine released 324.6, but selenium only released 195. Okay? So that is the one. So if you really understand ionization energy, these two is not very hard actually. These two are not very hard. So let's make a final summary before we jump into calculation. So this is the final summary. Okay, let's do a final summary here. Okay, so electron affinity, you want to receive electron. Okay, so first electron affinity, it's negative. Second electron affinity, and so on, positive. Okay, so what else we need to know? When we look at the periodic table, we normally focus on 2 groups only, group 16 and group 17. But if you look at other group, also the same. When you're moving down the group, electron affinity become lesser. Why? Going down the group, more and more shells, electron far away from nucleus, you have a greater shielding effect. So due to this, the electron and the nucleus will form a weaker attraction. When you form weaker attraction, you release less energy. So that's why electron affinity become lesser and lesser. Okay. Then we also learned a moment ago, when you move across the period from the left to the right, electron affinity increases. Okay, why? When you move across the period, you have more and more proton inside the nucleus. More proton, which means that you have a greater nuclear charge. Greater nuclear charge means you have a stronger pulling force. When you're able to form a stronger attraction, you will release more and more energy. Okay, so with that being said, we are all done with electron affinity. Can you please let me know in the chat box, are you okay with this concept so far? Okay, awesome. All right. So now let's go to the blockbuster, the main thing for today's lesson. So the main thing for today's lesson is what? Remember, I said early on today, the main purpose for today's lesson is we want to know how to calculate lattice energy. We need to learn how to calculate lattice energy. Okay, so this is the main thing. All right. So, but we must understand atomization. We must understand electro affinity before we can do the calculation. And you will see why in a short while. Okay, so let's look at it. So now I want to introduce you a new thing called Born-Haber cycle. So actually, what is Born-Haber cycle? What is Born-Haber cycle? Born-Haber cycle is the more advanced version of the Hess law that you learned back in your AS. Now, remember in AS, under the chapter chemical energetics, we learn about Hess law. Okay, so this Born-Haber cycle is the Hess law, but go in more advanced version. Okay, it's the advancement of it. Just like, okay, I use a simple mathematics language to tell you lah. All right, just a simple thing lah. If you are, when you back in your so-called lower secondary, when you back in lower secondary, you only learn this x plus 7 equal to 0. What is this? This is called linear. Okay, linear algebra. So when you go on to your higher secondary, okay, like year 10, year 11, or if you're from SPM, which is Form 4 and Form 5, so you learn about a more advancement like x power 2 plus 3x minus 2 equal to 0. Okay, x power 3, blah, blah, blah. Okay, you learn about quadratic, you learn about cubic function. It go more advanced. Okay, same thing even when you learn your differentiation, also same thing. You learn the basic differentiation is dy dx. That's the basic differentiation. The more advanced is two times. Okay, right? So d square y dx square. So this is the second derivative. Okay, so this is called the more advanced version. So same thing goes to chemistry. The basic algebra is called Hess law. So now the advanced version is called Born-Haber cycle. Born-Haber cycle. So Born-Haber cycle got two versions. One is the simplified and one is the full version. But starting from year 2022, you don't need to learn about the full version anymore. Okay, you don't need to know the full version anymore when you starting from year 2022. Okay, you only need to know the simplified version. Okay, only focus in simplified version for your A2 syllabus. Full version, no longer there. That's why if you look at those earlier past year, like 2015, 2016, 2018, you might see some very complicated Hess law, complicated Born-Haber cycle. So at that time, they are still using the full version, okay? But now, we just focus on the simplified version we'll do, okay? So let me show you how to do the Born-Haber cycle, okay? How to do the Born-Haber cycle in a simplified version. So there is always a template. Template means a format. There is always a format that you need to fulfill. You must follow a format when you want to do Born-Haber cycle, okay? So now, let me put all the puzzles together first. Okay, first and foremost, when I need to use Born-Haber cycle, I use the Born-Haber cycle if and only if the question asks me to do a calculation related to lattice energy. Okay, what do we mean by related to lattice energy? They might give you something, they ask you to find lattice energy, or they might give you the lattice energy and ask you to find the missing part, the missing information. That's it. So two things. It's either when the question asks you to find lattice energy or the question give you the lattice energy, you can use Born-Haber cycle, okay? Whenever the question is related to the lattice energy, you can go to use the Born-Haber cycle already, okay? So let's look at it. So let me show you this, okay? Let me show you this. So when you want to do Born-Haber cycle, you must always follow this template, okay? I will use two examples as demonstration in a short while. I will use two examples here to demonstrate what it is, okay? Then if the time allow, probably I'll do some past year question with you guys so that you can imagine how it works, okay? So let's look at this. So this is the template. This is the template. So when you want to do Born-Haber cycle, you always want to draw a triangle. I want you guys to always draw a triangle when you want to go for Born-Haber cycle. The first part of the triangle is here, is called the gas ion, okay? So you want the gas ion. The second part of the triangle, which is here, is solid ionic compound. Okay. So the third part of the triangle is the bottom is element, the raw material. Okay. So now let's connect this triangle together. Okay. So gas ion can combine together to form solid ionic compound. What is this? This is something we learned in the first lesson, lesson number 1 for your A2 syllabus. When gas ion combine together to form solid ionic compound, we will get lattice energy. Okay? Okay, next one. From element to become solid ionic compound, what is it? Okay, always remember, element means raw material. Raw material become a compound, not a compound become raw material. The arrow is very important. The directions of the arrow is important. This is something we learned in AS. When you given raw material, okay, and you want to join the raw material, the element, when you give an element, you want to join the element to become something else. This is called enthalpy of formation. We learned this in AS, okay? Element joined together form a compound is called formation, okay? All right. So then the last thing, element can transform to gaseous ion. Okay, you can change the raw material to gas ion. This is more complicated. This is very complicated. I put 5-star here. This is very complicated. So from element to gas ion, it involves multiple steps. Okay, although you only see one arrow here, actually it got many steps. I'll show you later. Okay, all right. So this one, I use a symbol. We can put it delta H1. So some student will ask, Mr. Martin, why we must put delta H1? This is just a formula they put in the books. That you can use other symbol one. Some people say, sir, can I put delta H2? Yes. Can I put delta H3? Can. Can I put delta HW? Whatever it is also can. Okay. But to be safe, to be secure, but it's always better to follow the format they give you in marking scheme or they give you in textbook, which is delta H1. That's why I always make it become delta H1. Okay. So this will be the format. Okay, this will be the Born-Haber cycle template that you need to use. So every time when the question asks regarding lattice energy, no matter they give you lattice energy, ask for something else, or they give you some information, ask you to calculate lattice energy, I know I need to use Born-Haber cycle to calculate. So when I want to do Born-Haber cycle, the first thing I do is I fill in this triangle. I always fill in this triangle and draw this diagram first. Because if you don't know this diagram, no matter how good you are with pressing the calculator, you are not going to get the answer. So most importantly, always draw the diagram first. Okay, so the best way to learn is by example. Okay, the best way to learn is by example. So I will try to run through 2 examples. Okay, I will do 2 examples with you guys. So hopefully you all can get some idea. Again, when you first started, you might find it very weird, very awkward, very hard to catch up, but you will be fine. Okay, so you'll be fine. Just follow me step by step. You will be fine. Okay, and then next lesson, I'll do a lot of past year question with you all. Then you all can see exactly how to apply the Born-Haber cycle. Okay, so let's start with 2 simple examples first. So I start with the first example. First example is a very easy one. So let's look at this. The question say, use the following data, which is here. They gave us 5 data, and they asked us to use the data here to calculate the value for lattice energy. So this is the calculation for lattice energy. We want to find the lattice energy for sodium chloride. Okay. So as usual, when the question is all about lattice energy, you like it or not, okay, when you have a calculation that is related to lattice energy, always go for Born-Haber cycle. Okay, always go for Born-Haber cycle. So let's do the Born-Haber cycle together first. So when you want to use Born-Haber cycle, you must follow this template. Okay, always use the Born-Haber cycle template. Yeah. So we have gas ion on the left, we have solid ionic compound on the right, we have element at the bottom. Don't change the sequence. Don't change the sequence. So let's try to do this triangle together. So first of all, we have gas ion. So what is the gas ion? We want to form sodium chloride. Sodium chloride got sodium and got chloride. So let's do it. Sodium ion is Na plus, chloride ion is Cl minus, and they are gaseous ion. As what I mentioned last lesson and today, in this chapter, state symbol is compulsory. I repeat, in this chapter, state symbol is compulsory. So we need to write the state symbol. So we have gaseous ion. So we need to be gas. Okay, so they combine together. So when gas ion combine together, you are able to get solid ionic compound. What is the solid ionic compound here? Sodium chloride. So sodium chloride is NaCl. So all the ionic compound, they are solid. Remember, state symbol is important. So put the arrow here first. Okay? So same thing. When gas ion combine to solid ionic compound, this is lattice energy. Do we know the lattice energy? No, we don't. This question wants us to find the lattice energy, so we know nothing about the lattice energy. Put a question mark here. Okay, up to this point, can you guys let me know in the chat box, are you okay with this so far? Okay, good. All right, so let's continue, yeah? Okay, so we're not done yet. We only fill up 2 corners of the triangle. We have one more thing to go. So at the bottom, we must fill in element. So again, what is element? Element means the material in their most nature form. Element means the raw material in their most, okay, nature state, okay? The raw material in the most nature state, all right? So now ask yourself, okay, what is the raw material you needed here? What is the raw material you needed here? Okay, so you see we have sodium, right? Sodium. So where you get the sodium from? Naturally, sodium exists as sodium metal, right? Naturally, in the most nature form, sodium exists as a metal. So metal is in a solid form. Okay, what about chlorine? Cl, naturally, Cl is not like this one. Naturally, chlorine exists as Cl2. Naturally, chlorine exists as Cl2. And naturally, chlorine is a gas. Okay, that's it. Okay, so these two is called element. This is the sodium in the most nature form. This is the chlorine in the most nature form. So after that, before you do any calculation, not to forget to balance the equation. One sodium on the left, one sodium on the right, one sodium at the bottom. Fantastic. One chlorine on the left, one chlorine on the right, two chlorine on at the bottom. So you need to put a half. So it is balanced already. Okay. So now the next thing you have to be careful with the arrow. The arrow come here or the arrow come here. Very important. So remember, raw material become compound, not compound become raw material. Okay. So this arrow very important. So what is this? When element join together to form compound, this is enthalpy of formation. Do we know the value for the enthalpy of formation? Absolutely. The question tells us, look at here, everyone. Enthalpy of, accidentally erase it. Enthalpy of formation is given negative 411. So negative 411 is given. Okay. So lastly, which is here. So from the element, you want to form the ionic gas. So you want to form the gas ion. This is the one. All right. So raw material becomes something else, not something else become raw material. So please Please be careful with the arrow. Okay, so this one, if you want to change the raw material become gas ion, it involves multiple steps. Okay, so we call it delta H1. Okay, up to this point, are you guys okay with how I construct this triangle? Are you guys okay with how I construct this triangle? Okay, can all right, can all right. So this is very, very important. So now always start with this template. Okay, only when the template is ready, then only we can proceed with the calculation. Okay, then only we can proceed with the calculation. Okay, let's proceed with calculation now. So now if you want to calculate this thing, so all right, sorry. Now if I want to calculate this thing, I need to find this one first. Make sense, ma? Okay, if you have a triangle, if you want to find here, you must know this one and this one. So this part, the value already given, which is -411. But this part, the value is not given. So I need to find it out. I need to calculate the value here. So how to go about it? So remember I said early on today, I say what? From this element, if you want to change to gas ion, it actually involves multiple steps. Okay, from element, if you want to change to gas ion, it actually involves multiple steps. I'll teach you step by step how to do it. Okay, I'll teach you step by step how to do it. Okay, so let me show you this one first. Okay, this is the notes ready already, but I'll show you step by step how to do first. Okay, so how to change element to gas ion. So we have two elements here. You can start from any one first. Let's say I start from sodium. So I want to show you guys how I change the sodium solid, which is the element, to become sodium gas ion in the end. Okay, I want to show you step by step how it can be achieved. So the first thing you should do is this. You should take the sodium solid to change to the sodium gas atom first. Okay, always get the gas atom first. Okay, always change whatever raw material you have to become gas atom first. So when you want to get the gas atom, what is it? Gas atom, this is something we learned early on today. This is enthalpy of atomization, isn't it? When you're getting gas atom, that is enthalpy of atomization. That's what we learned today. And remember, for enthalpy of atomization, the gas atom must be 1 mole. Okay? So do we know the value for the enthalpy of atomization? Yes. Look at what they give us. Come on. Enthalpy of atomization for sodium, it's 107 positive. Okay, so let's do it. So now we know already, atomization for sodium, it's positive 107. Done. So now we have successfully changed the sodium from solid to become gas. We're not done yet. So after we having the gas, we want the gas ion. Now we only have gas atom. So we need to change the gas atom to become gas ion. So what is this? So this is something we learned today. When you have a neutral atom, when you have neutral gas atom, you can remove electron and make it become gas positive ion. This is called ionization energy. When you have a neutral gas atom, you go to receive electron. This is called electron affinity. When you receive electron, you will get a gas and it's a negative ion. So you can see, now we are putting all the puzzles. We are putting everything we learned together now. So now what I want to do, I want to make something neutral to become a positive ion. So if you want to get a positive gas ion, if you want to get a positive gas ion, it is ionization energy. Since the charge is positive 1, so you need first ionization energy. So what is the first ionization energy for sodium? So the first ionization energy for sodium, it's positive 494. It's positive 494. So we know already, positive 494. Okay, so that's it. Okay, so please let me know in the chat box. Do you still able to follow? So far, so good? Okay, so we're done already with the sodium, so but we're not done with the entire thing because I only done with the sodium. I haven't done with the chlorine. So now copy. I want the half Cl2 to become Cl minus gas in the end. So let's do it. So I want the half Cl2. Chlorine is a gas molecule. I want to make it become chloride gas ion. So this is what I want to do. All right. So same thing, it involves multiple steps like this. So we write half chlorine gas first. So always change the raw material to become gas atom. Always change the raw material, become gas atom. So you want to change the chlorine to become chlorine gas atom. Okay. So this is the tips, huh? When you come to multiple step, always change your raw material. Your raw material is called element. Change them become gas atom first. Then only from gas atom, you change them become gas ion. Okay? If you want to change them become a positive gas ion, you go for ionization energy. If you want to change them become negative gas ion, you go for electron affinity. So that is the flow. That is the flow of the process. Okay? So we're going to do it together. So let's do it. So to change the chlorine to become 1 mole of gas atom, this is atomization. So what is atomization for chlorine is given here. Chlorine atomization, it's positive 122. So it is positive 122. So we have it. Okay. Then only we change the chlorine gas atom to become chloride gas ion. So to change a neutral gas atom to become a negative ion, what should be done? You see, neutral gas atom want to become negative gas ion. So we need to receive electron, that is electron affinity. Okay, so since the charge is -1, so it's electron affinity number 1. What is the first electron affinity? Is given. Electron affinity of chlorine given -349. So it's given -349. Okay, with that being said, we are done with the chlorine. Okay, let me know. So far, so good? Okay, can Okay, so now let me erase this. Okay, because actually I already written all these things in my notes lah. Just show you step by step. So you see, this is the one. Okay, so this is my notes. So element change to gas ion, which is here. This is the element. This is the gas ion. So here it involves many steps. So we change the raw material to become gas atom first. Then only the gas atom, we change them to become gas ion. And this red color is the energy that we get. Yeah. So what you should do now is that if you want to get delta H1 here, if you want to get delta H1, just add all the red color thingy. Just add all the red color number together. Just all this number, red color one, just add together. You were able to get this thing, delta H1. Okay, so let's do it. So if I add these 4 things together, which is here, I was able to get 374. So now I get delta H1 already. So once the delta H1, you got it. Now the triangle, you already know it. Now your triangle, this one don't know. This is -411. This is 374. Now you can do your calculation. So now you do your Hess law as what you learned in AS. I believe everyone should know how to do this. AS, how to do this. Okay. So this is like your mathematics called vectors, mathematic vectors. So if you want to find lattice energy, you want to go from here to here, right? From here to here, this is lattice energy. So you have 2 different paths. From this point to this point, this is the first path you can use, which is lattice energy. The second path you can use is this. The second path, you can go from here to here, then here to here. That is the second path, isn't it? All right. So according to the Hess law that we learned in AS, no matter which path that you are taking, the energy change is the same. No matter you are taking path 1 or path 2, the energy change is the same. So let's do the calculation. So how to calculate the lattice energy? So lattice energy, to calculate, you go for this path. So according to vectors, when I going down, what is the value? This one go up is 374. When you go down, mathematics, change the direction, change the sign. When you go down, this 374 become negative 374. That's it. So then after you go down here, then this one you go up. When you go up, what happens is, I want to go up, this original arrow also go up. So this arrow is 411 negative. So when I go in the same direction, I don't need to change the sign. I copy back 411 here. So I key in the whole thing to calculator, I'll get 785 kilojoules per mole. So guys, can you please let me know in the chat box, do you understand what am I talking about? Okay, this part got nothing to do with A2 already. This is a simple thing like you learn in AS. This is simple mathematics, we call it vectors. Okay, if you understand the concept of vectors, you shouldn't have a big issue on this. Okay? You shouldn't have a very big issue on this. Okay, we're done. Yeah, so now I'll show you one more example. Okay, I'll show you one more example. All right, to close up with today's lesson. Okay, so today's lesson, I just run through 2 examples. Then probably in the next lesson, I'll do a lot of past year question with you guys. Okay, I'll do about probably 4 to 5 past year question on lattice energy so that you can see yourself how to practice, how to apply the lattice energy calculation, how to use the Born-Haber concept to do the calculation in the real examination question. I'll do that with you all, okay, in the next lesson. For today, I just use 2 examples for demonstration. Okay, let's go for one more example. So one more example here. Okay, use the following data to calculate a value for the enthalpy of formation for magnesium oxide. So I want to find the enthalpy of formation for magnesium oxide. So this is formation. So this question, they give me lattice energy. They give me atomization of magnesium. They give me electron affinity of oxygen. Electron affinity of oxygen. So why they give me 2? Because there are 2 electron affinity. Okay, because oxygen receive 1 more electron become O minus. That is the first electron affinity. Then you receive another 1 more electron. Then you become O2 minus. So there are 2 electron affinities here. Okay. So these are the information they gave me. All right. So this question, not very hard, but it's a little bit tricky and not so straightforward compared to the first one. The first example, the first question that we discussed a moment ago is very easy. It's very, very straightforward. But this question is slightly more challenging. Okay, slightly more challenging. Okay, let's do it. So how to do this? So same thing like what I said, whenever the question is related to lattice energy, when I say related, it doesn't mean that you must calculate lattice energy. When they give you lattice energy, you also can use Born-Haber cycle. So please remember, when the question is related with lattice energy, related means they ask you to calculate lattice energy, or they give you lattice energy, ask you to calculate something else, you always can use Born-Haber cycle. So I will go for Born-Haber cycle. So when I decided to use the Born-Haber cycle, I always need to fill up this template. Okay, I always need to fill up the template before I begin with any calculation. So let's fill in the template. So what is the gas ion I need here? So I want magnesium oxide. The gas ion is magnesium and oxygen. So I do it here. Magnesium, 2 plus, gas ion. Oxygen, 2 minus, gas ion. So when they combine together, they will form solid ionic compound. The solid ionic compound is magnesium oxide. Here we go, magnesium oxide. Not to forget, you must write stick symbol, solid, okay? So from gas ion to become solid ionic compound, that is lattice energy. So the lattice energy value is given, which is negative 3,791. So I put the value negative 3,791. Okay, so now I'm done with here. So now I fill in the blanks for the last part of the triangle, which is the element. So elements, again, is the raw material in the most nature state, in the most nature form. So magnesium, what is the most nature form of magnesium? Magnesium is a metal. Metal exists as solid. So the most nature form of magnesium is Mg and is solid. So what is the most nature form of O? Oxygen never appear as O2 minus naturally. Naturally, oxygen is not exist as O2 minus. Naturally, oxygen exists as oxygen gas, O2. Okay, O2. Okay, so this is a gas. So not to forget, you need to balance the equation. One magnesium on the left, one magnesium on the right, one magnesium at the bottom. So one oxygen on the left, one oxygen on the right, two oxygen at the bottom, two oxygen at the bottom. You need to put a half here. So you put a half times 2, you become balanced already. Okay, then we fill in the blanks. So raw material can become gas ion from here to here. This is delta H1. Delta H1 got many steps that we will do later. From here, raw material become compound. When raw material become compound, that is enthalpy of formation. So enthalpy of formation is something that we are looking forward. It's something that we want to calculate. We don't know. This question wants us to calculate the enthalpy of formation. Okay, so let's see how it works. Okay, let's see how it works. Okay, let's do it. Okay, so up to this point, are you guys okay with how I construct this triangle? Are you guys okay with how I construct this triangle first? Okay, so once the triangle is ready, then we can do the calculation. So now we always focus on this part, the multiple step. So remember again how to do the multiple step. This is element, this is gas ion. So let me revise in 1 minute again. If you want to change from element to gas ion, it involves multiple steps. How you do the multiple step? You change the element, which is the raw material, all the way to become gas atom first. So when you change raw material become gas atom, that is enthalpy of atomization. Then the gas atom, you want to make it become gas ion. So your gas ion, you have two possibilities. It can be a positive or it can be negative. So if you want to change the gas atom to become positive ion, you need to donate electron. So donate electron is ionization energy. So if you want to change the gas atom to become negative gas ion, you need to receive electron. When you receive electron, that is electron affinity. So that's what I keep mentioning today. We are combining every single piece of puzzle that we learn together. Okay, we are combining everything that we learn together into this calculation. Yeah, all right. So if there's any part you're not sure or don't understand, please ask, okay, or else you're going to find it very confusing. So let's start it. So I'll do it from magnesium first. Okay, so listen carefully. This is very interesting. Okay, so let me show you the magnesium first. So magnesium solid, I want to make it all the way to become magnesium 2 plus gas in the end. Okay, so how to go about it? So let's start with this. Magnesium solid is the raw material. Always change the raw material to become a gas atom. Always do that. So when you want to get the gas atom, this is enthalpy of atomization. Enthalpy of atomization for magnesium is given. Okay, atomization of magnesium is given, which is 148. So we go for it. 148. Positive. Then from the magnesium gas, you want to get Mg2 plus, right? Okay, listen carefully, guys. There's no way you can change Mg to become Mg2 plus directly when you do the calculation, okay? Because remember, when you want to change the gas atom to become gas ion, you need to do ionization energy. So ionization energy, every time you remove 1 mole of electron only, every time you remove 1 mole of electron only. So when Mg, you remove 1 mole of electron, it becomes Mg plus. Then only Mg plus remove 1 mole of electron again to become Mg2 plus. So you cannot cut short. You cannot cut short on Mg all the way become Mg2 plus. No. Okay. You need to remove electron 1 mole by 1 mole. Remove 1 mole, make it Mg plus first, then only Mg2 plus. Are you okay with this concept? Can you let me know in the chat box, are you okay with this concept? Okay, can so now listen carefully. Now, this is where we need to be careful. When you want to get positive ion, you need ionization energy. If you want to get positive 1, that is first ionization energy. When you want to get positive 2, that is second ionization energy. But what's the problem here, everyone? Look at the data given. Do they give us the ionization energy for magnesium? The answer is no, they didn't. They didn't provide us the ionization energy for magnesium. So what should we do? So that's the difference between example 1 and example 2. Example 1, they spoon feed you. Okay? They spoon feed you. They give you all the information directly. You just use it. But don't expect they will do this every single time. So in this question, they didn't give us the ionization value for the magnesium. So what should we do? So if they never give us the information, go to your data booklet. Go and refer to your data booklet. So look at the data booklet. Okay, this is the ionization energy. Okay, you look at it. This is the ionization energy. Yeah. So what we want, magnesium. So let's go for magnesium. So magnesium, this is the first and second ionization energy. Magnesium, the first ionization energy, 736. Second ionization energy, 1,450. So these two values, we have to get it ourselves. So that's why you see here, everyone. So the first ionization energy for magnesium is 736. Second ionization energy for magnesium is 1,450. So these two numbers, these two values, these two figures are not given. I get it myself. Where I get it from data booklet. Okay, so now I am done with magnesium already. Okay, so now I need to do the next thing. I need to do the second thing, the oxygen. So same thing. Now I want to change the raw material oxygen, which is this fella, half O2, to become O2 minus gas ion. So I want to do this. Half O2 gas, I want to make it become O2 minus gas ion. So same thing, this process involves multiple steps. So I want to do the multiple step with you all. So how to do it? So we copy the half O2 first. Always starting with changing the raw material to become gas atom. So oxygen, gas atom. So if you want to get the gas atom, you need enthalpy of atomization. So now look back for this question. Do they give us enthalpy of atomization for oxygen? No, right? They only give us atomization for magnesium. They didn't provide us with the atomization for oxygen. So we are in trouble. We're in trouble. So what should I do? So when they never give us enthalpy of atomization, what should I do? So recall back what we learned early on today. Okay, let's recall back something we learned about an hour back. Okay, so this is the one. If they never give us the enthalpy of atomization, we can use the data booklet to find the bond energy and take half of the bond energy to calculate the enthalpy of atomization. That's why I say we are putting all the puzzles. We are using whatever thing we learned today to do the calculation. So that's what we want to do now. Okay, this is what we want to do now. So let's go on. So for this question, they didn't give me the enthalpy of atomization for oxygen. So I need to take half of the bond energy to calculate myself. So what should I do? So I need to find the value from data booklet. So let's do it. So let's go for data booklet, everyone. So this is the bond energy, yeah? So oxygen O2. So oxygen is O double bond. Oxygen is double bond, so which is here. So oxygen, the bond energy, okay, is 496. Okay, so we take this value, half times 496. Okay, that is how we get it. All right, then the next thing, From oxygen, you want to become gas ion. You cannot change O to become O2 minus immediately. No way. Because no matter donate or receive electron, we only can go 1 mole only. So when you receive 1 mole of electron, become O minus gas. You receive 1 mole of electron again, it become O2 minus gas. Okay? So that's it. When you're receiving electron, that is electron affinity. So when you receive the first electron to become -1, this is first electron affinity. When you become -2, this is the second electron affinity. So the first and second electron affinity, the value is given here. This is the first electron affinity. This is the second electron affinity. These are the numbers. So now you put everything here, you see? All right, now you have already, okay? Enthalpy of atomization. You will take half of the bond energy, I do it. So first electron affinity given, second electron affinity is given. Okay, so then how I get the delta H1? So all these multiple steps, all the red color thingy, I add together. Okay, when I add everything together, I get 3,239. Okay, I'll take a break here. Are you okay with this concept so far? Okay, so guys, you can see it's not very hard, isn't it? But it is tedious, isn't it? It's very, very tedious. You have to do it slowly. You have to do it carefully. Okay, don't keep on thinking of doing shortcut. I rather you do it slow but carefully. Okay, do it slow and carefully because it involves so many steps. Okay, if you're careless, you will lose a lot of marks. Okay, so now you already get the value for this fella. So then you go back to this triangle again. So take a look on this triangle again. So now, this one, you have the value. This delta H1 we calculated moment ago. So now you only want to find here. So quite simple lah. Then you can do your mathematics again. Okay? Then you can do your mathematics. So how to find this? So let's do your mathematics, the Hess law, okay, vectors. So I want to find delta HF, which is from here to here. So from here to here, this is delta HF. So how I calculate it? So this is starting point. This is the finishing point. So this is the first path I can use. I can use this path, or I can go the other way around. I also can use another path. Okay, I also can use another path. I also can take this path. I can come here, then only go here, right? So what should I do? So if I go here, what should I do? If I go in this direction, I follow the same arrow here. So I don't need to change the sign. I copy back 3,239. Then if I go here to here, same thing. If I go here to here, I also go in the same direction as this arrow. So I don't need to change the sign. I copy back -3,791. So key into my calculator, my final answer is -552. Okay, so by doing that, I already obtained the final answer for the enthalpy of formation. So my enthalpy of formation, it's -552. Not to forget, when you do chemistry calculation, please, please, please not to forget to put in your unit kilojoules per mole. All right? So that is how it works. So can you type in the chat box and let me know, are you okay with how does this calculation works? Okay, so I don't think it's really hard, like what I say. Every time when you see a question, the question is related to a Born-Haber cycle, always go, sorry, when the question is related to lattice energy, always go for your Born-Haber cycle. When you want to do Born-Haber cycle, always construct your triangle first. Okay, then after construct a triangle, go to find your delta H1. Change your element to become your gas ion. Involve multiple steps. Okay, do it step by step. So element, you need to change to gas atom first, and only change to gas ion. So make sure you know all the steps that I show you. I mentioned many times, and I want to emphasize again, don't keep thinking of shortcut. Do it slowly, do it carefully, do it step by step. Okay, So once you're able to fill in all the information, then you're able to calculate the unknown. As simple as that. So it's not very, very hard. Okay? And this question of Born-Haber cycle is considered quite popular in the A2 exam. You shouldn't have a big issue if you really, really follow the instruction. Follow the instruction, do it step by step. And you see, sometimes they are very bad. They don't give you the ionization energy. Where to find it? Data booklet. So sometimes they don't give you the atomization. So if they don't give you atomization, take the bond energy from data booklet and multiply by half. Okay? So these are something very, very important. Okay? So I hope you can see, okay, how it works. Because some of the college, they cover this entire Born-Haber cycle in 15 minutes. I have heard from some of my ex-students, their college actually can finish the entire Born-Haber cycle in 15 minutes. Okay, in the end, everyone was so blurred. Everyone got stunned. What is happening? Yeah. So I spent quite some time to cover that. But I hope it worth it as in you really can understand how it works. You really can see a big picture. Okay. You will understand even better when I show you some past year question that is related to Born-Haber cycle in lesson number 3. Okay. In our next lesson, I'll show you some past year question that are related to this particular concept. Okay, then you can see exactly how to apply, how to solve the question using the right concept. All right. Yeah, so I think that's all. Okay, that is everything that we need to learn for today's lesson. All right. So I'll see you in the next lesson then. Yeah.